Hey, hello there. So let's talk about this question 548, split array with equal sum. We have a integer array and we want to find if there are triplets, three values ijk, satisfy the following condition. The second condition basically says if we take out I, take out j, and also take out k, the four subarrays has to sum up to the same thing. And the first condition is just a guarantee that if we take out ijk, we actually have some elements we at least have one element in each one of those subarrays. So since we are actually taking out these three values, there's no way we can know ahead of time how much this four subarray gonna sum up to. So we have to do calculations of that and testing. So that's for that reason we want something that can facilitate us to check the sum from 0 to I minus 1, sum from I plus 1 to j minus 1. So to do that we can do the prefix sum, summing all the numbers from 0 to certain location 0i, and just store that value for all the i's, all the possible ending points. So for any kind of subarray, we just look up two numbers from there and do a subtraction, so we get a constant time calculation to sum all the subarrays. So if we have that, we can do a brute force solution, which is going to be for I in something, some range, for j in some range, and for k in some range. We try to look at 0 to I minus 1, I plus 1 to j minus 1, j plus 1 to k minus 1, and k plus 1 to n minus 1. So four different subsections. If they are all equal, we return true. So the time complexity for this is going to be cubic. It's not going to pass all the test cases, unfortunately. So we have to look at where are the redundancies. So one thing we can really quickly add is we're going to test the third loop. We don't really need to run it if sum of 0 to I minus 1 is equal to sum of from j plus 1 to from I plus 1 to j minus 1. Only if this is true, we want to take a look at the possible case that's dividing the remainder array into two parts, and have to see whether the four parts actually sum up to the same thing. So that can save slightly a little bit, but it's not gonna save the day because there are redundancies in the I and j here. What could be the case? So let's say that we fix the j. What if there are multiple i's there, both satisfy this condition? And whenever that satisfy the condition, even though they sum up to the same thing, we still run a full search for the k. So that is redundancy. So let me actually just demonstrate this really quickly with a dummy example. We have something like this, and j is currently here. So I could be pointing at any one of these zeros, so that from 0 to I minus 1 is equal to 4, from I plus 1 to j is also equal to 4, but even though they are essentially the same thing. And for all of these repetition cases, we have to do, even with this testing, we have to do this k search, which is going to be really redundant. So for that reason, we want to get rid of this extra work. So how do we do this? We actually want to just group this. So all we care is that if we have a given j, at this location, all we care is what values we actually sum up to that's equal. We don't care this I. All we care is that this is equal to this, and we also want to remember the value. After that, we're just going to search for k. So the way we do this is actually gonna change the order of the looping for j in some range, and we want to do is for I in a relatively limited range, and we're gonna cache if we do find a I that can partition the first 0 to j position into two equal halves, we're gonna save the sum, and then we can do a parallel for loop to search for the k. It should be k minus 1, k plus 1 to n minus 1 equal to one of the sum from the loop here. So yeah, so this reduced the runtime from cubic into square time, and we made this transformation by observing that there's not only unnecessary work if we don't do this testing. Also, based on the ij, there could be duplications. So we want to eliminate those, or rather, we don't care about the I. All we care is this. So we summarize all those cases into one single number in the set. So that gives us this runtime complexity reduction. So yeah, so just gonna code this up really quickly. I think you get the idea, and it will be pretty simple. Get this nums and do the prefix sum. We're starting with the first number, and just gonna start to add number and append to this. And then we're just gonna do according to the kind of a procedural code I left out there. So the j is gonna starting with 3. Let me actually just grab the example, and it can help us to work out that this range is a lot better. We have this index to be 0, 1, 2, 3, 4, 5, 6. It's quite tight here. I is at 1, j is at 3, and k is at 5. And since that their n is equal to 7, we see the j's possible range as small as possible, that would be 3, and as large as possible, this is also as large as possible, which is 7 subtracted by 4. So this is 3, which is equivalent to 7 subtracted by 4. Since that the Python range, the right hand side is exclusive, we have to use this number, so which is going to be 7 subtracted by 3, which is n subtracted by 3 here in our case. And we're gonna use a set to cache all the sum values that we can get by using an I to partition from 0 to j minus 1. That's gonna be in our targets. I's range is from 1, that's the leftmost possible, and the largest it could be is j subtracted by 2, and for that reason the right hand side is j minus 1. So we get the sum from here, which is going to be looking up directly from here. We are including I minus 1, so it's going to be I minus 1. L2 is going to be some L1, some L2. Just be a little bit more readable, I guess. So this second sum is from I plus 1 to j minus 1. So that's looking at this number with this j minus 1 included, and subtracted by the sum from 0 including I. So the difference is going to be j plus 1, I plus 1 to j minus 1. And if these two sums are the same, we're going to add this sum to the set. It could potentially be just one of the target that we're looking for when we try the case on the right hand side. Then we do the same thing for the k. The range is going to be j plus 1 to j plus 2, right? Yeah, because j plus 1, we couldn't really take that. It has to be at least the 2 larger. Left hand side is included, right hand side is not included. The right hand side would just be n minus 1. Yeah, n minus 1, because we choose 6 here because it's exclusive. So if we put 6 as the right hand side, the largest that we can take is 5. Yeah, this example really helps. So we're just going to do the two sums for the right hand side. The sum of R1 is going to be this, j plus 1 to k minus 1, which is going to be k minus 1 subtracted by summing from 0 to j. The remainder is going to be from n minus 1 to k, subtracted by k. So that's the two sum on the right hand side, and we want to check if they are the same, and also the same value has to be in the target. So yeah, so this is the code, the square time code. Yeah. Let's say if we are exploring the midpoint, and what's happening here is we actually want to, what we're doing is to summarizing, grouping the all the cases here about the potential I that can divide this 0 to j into two equal sums. So this is grouping. It has a little bit the functionality of grouping, so be able to reduce the time complexity. And this is just checking. So yeah, so this is the solution. It's square time and n squared time, and the space complexity, this is the order of n, and the set here is definitely less than half of the size of the, not definitely half. What's if j is very towards the end, and every sum is so different, and we have a lot of anyway, it's definitely less than linear, the targets here, definitely less than linear of the array, size of the array. So it's a linear space and square time algorithm. We can get here by looking at the triple loop solution and the reasoning about the duplication in the two loops here, in the first outer two layers of loop there. Yeah, so that's this question.